So, very good evening to everyone. Today, covering the C3 compounds that we can derive from the petroleum in industry as a petrochemical product. In the last class, we have discussed about the C1 and C2 petrochemical products. So, in this class, we will be covering C3 petrochemical products. So, let's move on to first slide. So, what are the chemicals that we can derive from the C3 compounds that we enlisted as C3 compounds? Propylene, which is known as propylenes, are directly derived from the petroleum crude source. Processes within a refinery which gives gives the product as propylene are steam cracking of hydrocarbons. Important process is steam cracking of hydrocarbons, direct pyrolysis of propane. It also gives propylene as a product, and also we will get lot of propylene in the refinery of gases. So first on, as a C3 petrochemical product, we will be discussing about the production of isopropanol, which is C3 CH3 whole to CHOH. This is the chemical formula of isopropanol. So isopropanol, it is hugely used as an intermediate product for acetone and highly used in the multipurpose industries. What are the methods of isopropanol production? One is direct catalytic hydration of propylene. Another method available is hydration of the propylene via sulfation method and hydrolysis method. So we will be discussing this process. So now we will look what are the chemical reactions involved in the hydration of propylene via sulfation and hydrolysis process. First, the first step that occurs, that is sulfation process. In this process, propylene, it reacts with sulfuric acid and it gives some isopropyl acid sulfate, whose chemical formula is like this. Nothing but isopropyl acid sulfate. In the second step, hydrolysis occurs. So in the hydrolysis process, this isopropyl acid sulfate it reacts with water and hydrolyzed to some intermediate compound. And reproduce H2SO4. And in the last step, there is ether formation, which is considered to be a side reaction, in which there is also some diisopropyl sulfate diisopropyl sulfate. It also hydrolyzed and it forms ether. and also H2SO4 is reproduced. So it is an important product which is let me so this product, it is diisopropyl ethyl. So we have discussed about the chemical reactions which is involved in the hydration of the propylene via sulfation and hydrolysis process. It has three steps: sulfation. It has basically two steps: sulfation and hydrolysis, and one side reaction is also occurring, that is the ether formation. So we will now discuss about the flow chart to describe how the isopropanol is um, is produced by this method that we have just discussed. So we will start from this end where the refinery gas that has C2 to C3 carbon in the gaseous form, those are pressurized to 20 atmosphere, and that is fed to the sieved or tray kind of absorber. So in this absorber, what the refrigerated brine solution is passes through to maintain the temperature, because the first step we have discussed the sulfation process, that is a very exothermic in nature. So we have to maintain the temperature of this in this reactor, in this absorber. So we need to do this we need to recirculate the refrigerated brine solution. Now also in this absorber you can see there is 70% H2SO4 acid is we are adding. So we are adding this for the sulfation process. So here the main process that is occurring, that is the sulfation process, which is highly exothermic in nature. By the end of the sulfation process, we will get some light ends, and the also you need to notice that this absorber is operated at 20 to 25 atmosphere. So after the sulfation reaction is occurring, the solution is taken to the hydrolyzer, where the second chemical reaction that we have already discussed, that hydrolysis reaction is occurring. We are giving input of the water, and the hydration process is occurring, and as a byproduct we will be getting H2SO4, and that can be concentrated, and for that it can be sent to the concentrator to regenerate the H2SO4 acid. So after the hydrolysis reaction, we can see that the product is further taken to the caustic wash, where the rest of the H2SO4 acid can be neutralized by reaction with the caustic soda, and there the the effluent can be taken to the caustic storage and bleed, and we can also recirculate it for the next batch for the caustic wash. So after the caustic wash, the products are taken through the partial condenser, where the alcohol and ether can be condensed out and can be sent to the specific ether column, where in the ether column as a top product lightened, we can see that there is a separator where the water and alcohol layer, this layer is nothing but H2O and alcohols. These are bottom product can be recirculated back to the ether column for further distillation, and the more volatile isopropyl ether is recycled back to the absorber again. Further sulfation process. So this isopropyl ether is more volatile. That's why it can be taken from the top end product and can be recycled back. Whereas after the partial condensation, the gaseous product can be further water washed to remove the any acidic content and can be recycled back to the this can be recycled back and mixed to the feed of the process. So we now the point is the bottom product of the ether column has further heavy ends that can be fractionated through the isopropyl alcohol column. From here, the at the bottom product we can get water and heavy ends, and top product is further taken to the azeotropic distillation column. In the azeotropic distillation columns, we are getting top product as a isopropyl ether, and as a bottom product we are getting 99% isopropanol. You can see this from the isopropyl alcohol. As a top product we are getting here 87% isopropanol. For further concentration we are distillating through the azeotropic um, we are distillating through the azeotropic distillation process, where the isopropyl ether that is used as a azeotropic agent, and it can further try to concentrate the isopropanol, and the final product from the azeotropic column is 99% isopropanol. So this is the overall process of production of isopropanol by indirect hydration process. Moving forward, we will be discussing now the production of acetone. We know the chemical structure of acetone is like that: CH3COCH3. There is ketonic group, there is ketonic group, wait, no issue. So, in the chemical industry, there is a huge application of the acetone. So, we will be now looking at what are the method of production for acetone. The first method is catalytic dehydrogenation of isopropanol, or co-product of phenol process utilizing cumin, co-product of the glycerin, hydrogen peroxide process, oxidation of the propylene, what is known as Walker process, Also, the fermentation of the molasses gives or produce the acetone as a product. So among these all available methods, we will be discussing the first one for the method of acetone production. So now, what are the very basic chemical reactions involved in the catalytic and dehydrogenation process to produce acetone? So just now we have discussed about the isopropanol production. So that isopropanol is can be used as a raw material to produce acetone from it. The first reaction is isopropanol. It gives acetone. So here the dehydrogenation process is occurring. Also, another reaction that is occurring, it's oxidation, and that also gives acetone. So this is very simple reaction. Iso isopropyl alcohol. Also from the isopropyl alcohol directly by dehydrogenation and with reaction with oxygen it is produced acetone. So now we will discuss the flowchart to describe how the acetone is produced from the isopropanol. So you can see from the storage you are taking 88% of the isopropanol. So the isopropanol that we got as a top product before uh, introducing to the azeotropic distillation column, that is directly being taken for further processing or production of the acetone. So it is heated up by steam and then it is fed to the tubular catalytic reactor. Also you have to notice that this isopropanol from the storage, it is isopropanol vapor is compressed to 3 atmospheric pressure and then it is sent to the tubular catalytic reactor which is maintained at a pressure of 4 to 5 atmosphere and 500 degrees Celsius as a reaction temperature. Also to maintain the temperature, the flue gas is circulated to within the reactor to maintain the temperature. You can notice the catalytic reactor has catalyst silver or copper catalyst is used. So after the reaction, the product is taken for the water scrubbing, while the dehydrogenation process is occurring and hydrogen is taken out. The product is further taken to the acetone column where we want to separate the acetone from the mixture. So as a top product, we will be collecting acetone and the bottom product is still is again sent to the isopropanol column fractionator where the isopropanol is regenerated or the unreacted isopropanol is recycled back to the starting point or feed point. So this is very simple flowchart that is self-explanatory, just referring to the production of the acetone. Forward, we will be discussing now the production of the isopropyl benzene. So this isopropyl benzene is also known as cumene. It was first developed as a very high octane addition for the fuel oil, engine fuel. Like isopropyl benzene was added to the engine fuel for increasing the octane number of the fuel. The method of production of the isopropyl benzene, it is the propylene alkylation of the benzene. So this is the available method. We will be discussing this method. So now first let's see what are the chemical reactions involved in the propylene alkylation of the benzene, this process. So to produce the isopropyl benzene, we need the benzene first, then it reacts with the propylene, and then it forms cumene or isopropyl benzene. So this reaction, you can see this is a very exothermic in nature. This one is the main reaction. This one is the main reaction. Also, as a side reaction, we will get benzene plus n number of and forms it forms polyiso propyl benzene. So this is nothing but a polymeric reaction is occurring as a side reaction. But in the main reaction, our main product is cumene. So now let's move to the process description, how the isopropyl benzene is produced from the benzene. So in this project, we can see that the propylene flame, which are coming from the refinery of gas from the naphtha steam cracking plant, it is mixed with the benzene and then it is compressed to 25 atmospheric pressure and it is fed on from the top of the packed bed column. And here the packed bed column is stage wise. Okay. Now this reactor is maintained at a temperature of 250 degrees Celsius, and this is also and in this process the catalyst used is H3PO4 impregnated catalyst is used in the process. So to maintain the temperature, water or steam is used in the reactor. So as a product from the packed bed column, the product is taken to the first depropanizer. Depropanizer, the propane as a lighting is taken out from the top of the depropanizer column and it can be taken out as a product or can be recycled back, quenched and recycled back and again sent to the reactor. Because in the feed also we are supplying propane. Now the importance is the propane here added as inert and the dilution we have done by propane only to minimize the polycumene, like to minimize the polymerization reaction that we have just discussed, that there is side reaction that which is nothing but the polymerization reaction. So this polymerization reaction can be minimized the more we are doing dilution using the propane. So that's why you can see that recycle stream of the propane is sent at each and every stage as much as possible. Also, uh, this polymerization reaction can be minimized by using very high benzene to propylene feed ratio. Where I can write that important note that polymerization reaction can be minimized by keeping high ratio of benzene to propylene, and this high ratio it is like 5 or greater than that. So after that, uh, taken out we have took out the propane and then rest of the heavier portion is sent to the benzene column where the benzenes are regenerated and these are recycled to mix at a feed point, and the rest of the product is further sent to the cumene column where the top product is cumene we are having. But inside the reactor, if inside the reactor there is this benzene to propylene ratio is somewhat not up to the mark, then the side reaction polymerization reaction must be high enough, so there might be high yield of the polyalkyl benzene or mainly the diisopropyl benzene. So this can be minimized by using this high ratio, by keeping this high ratio. So that's all in the regarding the production of isopropyl benzene or cumene. We will discuss now the production of acrylonitrile. The chemical formula involved CH2CHCl. So this acrylonitrile, it is the cheapest of the acrylic monomer group and has a very good reactivity to the C triple bond cyanide bond and the double bond as well. And it is largely used as a polymer. So we will now discuss about the production methods available to produce the acrylonitrile, which is highly used in the polymer industry. First method is propylene ammonia air oxidation reaction, acetylene hydrogen cyanide reaction, ethylene cyanohydrin pyrolysis reaction, acetaldehyde hydrogen cyanide reaction. So these four various routes are available to produce the acrylonitrile. Now we will be focusing on the first process and we will discuss on how this acrylonitrile is produced by this process. So now discuss chemical reactions involved in the propylene ammonia air oxidation process. Very simple reaction, that is propylene, it acts with ammonia and also air and it gives acrylonitrile. This is also highly exothermic in nature. So this is the simple reactions occurring. So this is nothing but acrylonitrile. So now let's discuss about the production of acrylonitrile by that method using this flow sheet. So this propane feedstock which is coming from the refinery gas stream is mixed with ammonia and also the air and oxygen and it is pressurized and fed to the fluidized bed catalytic reactor. In the fluidized bed catalytic reactor, the pressure is maintained 1.5 to 3 atmosphere and the temperature is 400 to 500 degrees Celsius. You have to take note that it is a fluidized bed reactor and the contact time for the reaction is very less. It is of several seconds only. For as we already discussed, this is a very exothermic, highly exothermic reaction. So we need to make sure that there is proper water or cooling is being done to maintain the temperature inside the reactor. Now, to enhance the to perform this reaction, we need a catalyst, and this catalyst used for this reaction is molybdenum, bismuth, This material is used as a catalyst, which is moreover spherical catalyst of size of 0.01 to 0.03 nanometer size. Spherical porous. So here we can see that there are three reactants and a solid catalyst surface. This four ingredient is very necessary for high selectivity to produce the acrylonitrile as a major product. So from this steam, the product is further taken to the water scrubbing process, where the propane and nitrogen can be taken out and the water scrubbed product is further sent to the product splitter. Is sent to the product splitter. So from the product splitter, you can see the light ends it taken to the azeotropic column and it more produce the acrylonitrile as a top product, and heavy end some other products are there. As a bottom product, it is also taken to the azeotropic column and purifying column. Over the end, you will be getting acetonitrile as a top product. So these are some purification and azeotropic distillation process, this section. Other than that, whatever the reactions, the water splitting and this kind of thing, whatever, those are the products of this reaction which is occurring in the fluided bed catalytic reactor. Now you need to also remember one thing, that to get the more desired product, we need to minimize the sulfur content of the feed that we are introducing this end, because this sulfur can be highly reactive with the, like, it can highly degrade the catalyst performance over the period. So as much as possible, we prefer the desulfurized feed to be fed to the reactor. We will be discussing the next, which is the production of the isoprene. Polyisoprene, it moreover resembles to the natural rubber chemically, and it is expected to add more flexibility to the synthetic rubber. So that's why polyisoprene is important for making these synthetic rubbers. What are the methods those are available for the production of the isoprene? The first method is isomerization of the propylene dimer. Next one is the isobutylene formaldehyde reaction. Third one, methyl ethyl ketone formaldehyde reaction, acetone acetylene reaction, and also it can be produced as a byproduct of isopentane or maybe some dehydrogenation. So among these, we will be discussing the first process, that is isomerization of propylene dimer. So now let's discuss what are the chemical reactions involved in this process. First, the reaction is dimerization. Next one is isomerization. And last one is pyrolysis to produce the isoprene. We will discuss this in a new slide. Maybe it will not cover up. So here we were discussing that chemical reactions involved in process of isomerization of propylene. So the first process, that is dimerization. So here the propylene, it forms dimer, which is known as 2-methyl 1-pentene. So in this process, you have to maintain the process parameters of this high pressure, high temperature condition, and a catalyst of aluminum based catalyst. The next step after the dimerization, that would be isomerization. And in this process, that product, which is 2-methyl 1-pentene, is further produce isomer. This isomer is called as 2-methyl 2-pentane, and also it is happening in the presence of a acid catalyst at a process temperature of 150 to 300 degrees Celsius. At the last step, there will be pyrolysis. So in the pyrolysis, this isomer product or this isomer is pyrolyzed at a very high temperature condition, that is the condition of pyrolysis, in the presence of HBr catalyst, and it produces isoprene. and also it produced methane. So this is the overall chemical reactions involved in the isomerization process. We will now discuss the flow sheet for production of isoprene. So in this production of the isoprene, we are giving the feedstock of the propylene, and it is mixed with the tripropyl aluminum catalyst. That in the reaction we have seen, we have in the first step we have used some aluminum based catalyst. It is mixed and pressurized to 200 atmosphere, and then it is sent to the stirred tank reactor. As it is maintained as a very high pressure, so it is suggested that there is high propylene concentration in the feed. Also, you have to take care that the polar compounds are not present so much in the feedstock, because those are highly reactive to the catalyst that you are using, and so that can be catalyst degradation can be occurring over the period. So it is recommended to remove the highly polar compounds from the feed. So after mixing and compressing, it is sent to the stir tank reactor, that is a dimerization reactor. So here the temperature is maintained at 150 to 250 degrees Celsius, and also by this dimerization reaction we are getting conversion of 60 to 95% conversion. From this reactor the product is taken for the flash tower. The top product that has 2-methyl 1-pentene, that was the first reaction of the dimer product. 2-methyl 1-pentene we have discussed in the last slide for chemical reactions. The step A is following, and also some lighter hydrocarbons are there. So that is sent to the fractionator, C1 to C2 fractionator, where very light ends are separated out, and the bottoms are again sent to the C3 fractionator, where mostly the unreacted propylene which can be recycled back to the feedstock point. Further it is taken to the dimer tower, where we need to separate out the dimer, which is collected as a top product, that is 2-methyl 1-pentene. Then it is sent to the second step, that is the isomerization reactor. So in the isomerization reactor, that is a packed bed reactor, where we use some acid catalyst. So after the reaction, the product is sent to the stream splitter, where we are getting around 90 to 99% yield. So here in the isomerization reactor, we have already discussed the temperature is 150 to 300 degrees Celsius, and it takes lot of time, contact time, like few hours, and space velocity of 15 to 0.5. Whichever is not isomerized, the unreacted product is taken out as a top, and it is recycled back to the isomerization reactor again. So from the stream splitter, the bottom product is taken, that is 2-methyl 2-pentene, which is an isomer, and it is then fed mixed with the steam and fed to the tubular pyrolysis, that is the last stage. Pyrolysis reaction is occurring. So this reaction is very endothermic in nature, and we are giving around 600 to 800 degrees Celsius maintaining temperature, where the pyrolysis of the 2-methyl 2-pentane is occurring, and we are giving as a catalyst HBr catalyst we have used, and here the steam is used as diluent. Residence time is very less, zero point 0.3 to zero point 0.5 seconds residence time we are having. So the product is quenched out so that the HBr and quenched fluid can be recycled back, and the product is taken to the C1 tower where the methane or other fuel is taken out as a top product, and the bottom product is again taken to the purifying column where the top product is collected isoprene that we are requiring, and the bottom product is some other polymers can have. So this is the overall production method of isoprene from the propylene feedstock. The next process we are going to discuss, that is the production of propylene oxide. Propylene oxide, this has versatile application in making polyurethanes, propylene glycol, propylene glycol ethers, polypropylene glycol, etc. So the method of production involved for propylene oxide, one is chlorhydrin route and another one is direct oxidation. So we will be discussing the first method for production of the propylene oxide. Very simple reactions is involved in the process. Step 1, that is chlorhydrination process. Here the propylene react with HOCl and it forms intermediate product. The next one, the next method is dehydrochlorination, where this product is reacted with the calcium hydroxide and it forms the propylene oxide. Calcium chloride as a byproduct. So this one is so this one, it is propylene oxide. Simple reaction, chlorohydration and dehydrochlorination. Two processes are involved. So we will then discuss about the production of the propylene oxide through this flowchart. So as a reactant, we must have propylene, chlorine and water. These are fed to the packed tower column. Here, to maintain the temperature, the water circulation is made properly. These reactants are very important and they form chlorohydrin. Formation of the hypochlorous acid, that is HOCl, that reacts rapidly with this propylene. Already shown the reaction. Now this reaction is highly exothermic in nature. So from the top product, it will be NOH scrubbed and after that the propylene can be recycled back to the feed point. The other product, the main product that will be taken to the caustic wash, where the unreacted propylene will be scrubbed out. And also the byproduct CaCl2 waste will be separated out. Then the product is taken to the water splitter. Now you have to take care of the thing. Okay, so water splitter. So water that from the bottom the tar is being collected as a heavy end. So and at the last unit, that is the oxide purifier, from the top we are getting our desired product, that is propylene oxide, and undesired some product, those are polychlorides. So this section is somewhat in the packed tower. We are having chlorohydration. And here, by the using of the caustic calcium oxide basic treatment, we are doing dehydrochlorination because we are precipitating out the calcium chloride waste. So in this reaction, the reaction temperature is maintained at 50 degrees Celsius. We need to take care that the chlorine and propylene ratio in the feed to be chosen like that the liquid effluent contains 4 to 5% of the chlorohydrin that is produced out of these reactions, right? And the yield of the chlorohydrin is 87 is around 87 to 90%, and mostly the byproduct will be propylene dichloride. So this is the simple process, very simple flowchart. I guess you have understood this one. The next process is OXO process. So we will discuss this important process. Let's discuss the general what is OXO process. So an OXO process involves the substitution of the HCHO bond across a double bond. Hence, it is known as hydroformylation. The reactants which is involved in the OXO process, those are olefins and synthesis gas. The catalyst used in the OXO process, that is cobalt carbonyl. The primary product of the OXO process is aldehyde with additional carbon atom. Aldehyde group may be hydrogenated to form an alcohol or may be oxygenated to form an acid. So chemical reactions involved in the OXO process. First one is addition reaction, where simply Cn it turns out to be Cn plus 1. And next one is the dimerization reaction, where the zinc here the cobalt or salt as a catalyst is used, and dimerization reaction where the zinc salt as a catalyst is used. And in the dimer what happens, Cn plus 1 turns out to be C2n plus 2. The dimer forms. So we will quickly discuss some thermodynamic aspects of the OXO process. The The heat of reaction for the first process, that is hydroformylation, is around 30 to 35 kilocalorie per double bond. For propylene hydroformylation, you can see this is a exothermic nature because del H is negative. The best reaction yield can be achieved at a low temperature and high pressure condition, but the reaction has a favorable equilibrium constant at 200 degrees Celsius and 1 atmospheric pressure. The chosen catalyst for the um, addition chemical reaction first step, that is cobalt carbonyl, that can only form a high pressure condition, so that's the reason the reaction happens at a very high pressure, 100 to 250 atmosphere. Now we will see the oxo processing of the olefins or synthesis gas, that is the butanol production basically by oxo process. So how it is happening? The first step is aldehyde step. Here it's react with the same gas and either it forms, which is around 50% production of yield. It is also 50% production. The second step is the alcohol step. The reaction involved at the presence of nickel catalyst. So now we will be discussing the butanol production by this flowchart from the propylene by this oxo process. So now butanol production from the propylene by oxo process. This propylene as a feedstock we are introducing to the plant, and equimolar of propylene and hydrogen is also introduced. It is then pressurized, highly pressurized, and then it is sent to the reactor. Now it is compressed up to around 250 atmospheric pressure. and it is sent to the reactor. But the cobalt catalyst is used for the step of the hydroformylation. This cobalt naphthenate also added to give the 0.5 to 1% cobalt in the solution. So after the reaction happened, the solution is taken out and it is sent to the dimerization reactor, where the zinc modifier is added for the dimerization reaction to be occurred. Here, possibly the reaction can be, the catalyst can be recycled out from the reactor after the reaction. Then the product is sent to the liquid fraction, then sent to the reactor where it is mixed with the steam. At a temperature is maintained at 180 degrees Celsius and pressure of 2 atmosphere, comparatively low pressure as a 20 atmosphere, which is comparatively high pressure condition. And then it is decomposed cobalt carbonyl and naphthenate on the porous cobalt carrier. Then the product is taken to the hydrogenator, where the unconverted synthesis gas from the oxo converter can be before that it can be recycled back. This synthesis gas can be recycled back unconverted. So in this reactor, what is happening, the butyl aldehyde can be fractionated for product cells and continuously hydrogenated using the nickel catalyst. Hydrogenation is taking place uh, in this hydrogenated reactor at a pressure of 100 atmosphere and temperature of 150 degrees Celsius. Then the resulting product is taken out as a light end product. So you can see from the this uh, this table, you can see that products that is butyl aldehyde, which is produced nowhere in the dimerization and hydrogenation, but butanol that is produced by the hydrogenation process. Octyl aldehyde is produced in the dimerization process and octyl alcohol is produced in the broth process. So this is the overall butanol production from the propylene by oxo process. So we generally face major engineering problem regarding the cobalt balance in the process. The first problem, that is cobalt carbonyl, is highly soluble in the hydrocarbon liquids. So the cobalt carbonyl on the cobalt on the catalyst surface will be should be stripped. Like it would be stripped very soon. This is avoided by adding the soluble cobalt naphthenate, but metal ion has to be removed by decobalting unit. If the metal ions are not removed, then metallic slug may form in the downstream equipment that may also affect the process in the over long term. Small portion of the carbonyl is carried out of the reactor with unreacted synthesis gas. Those are recycled back and that should be washed out before mixing to the fresh feed condition. So now we will be more focusing to the C4 compounds. Now what are the chemicals that can be produced from the C4 compounds? The raw materials is butane and butylene. We can have butene epoxide from their butanoamines can be produced, butadienes in the rubber plastic industry, butanol, butyl acetate, it can be used for solvents, methyl ethyl ketones can be also produced from the butanol. Now this butanol production we have already discussed, it can be done by oxo process. Now first we will focus on the production of the butadiene. So butadiene is majorly used in the synthetic rubber manufacturing industry. Butadiene also used to supply it from earlier point of view. I'm telling that butadiene was used to supply it from the petroleum refinery operations by the or by the fermentation of the alcohol dehydration process. But now there are other methods too. The method of production for the butadiene, one is dehydrogenation of the butane, that which gives very high yield of the butadiene, dehydrogenation of the butylene, dehydrogenation or dehydration of the ethanol, and steam cracking process of the hydrocarbons. So mainly we will discuss first butadiene production by dehydrogenation process of the butane. The reactions those are involved in the process of dehydrogenation of butane, that is butane, it gives butadiene and hydrogen. Dehydrogenation process, it is endothermic process. This is the main reactions that we are talking about. Apart from that, there are some side reactions that butane it forms in butylene. It forms in butylene plus hydrogen. In the dehydrogenation process itself, it is producing some side reactions. N-butylene is produced. So now we will be discussing the production of the butadiene flowchart to describe the process. You can see that this C4 to C5 feed, which is largely containing N-butane, is preheated with the fuel gas. It is preheated and then it is mixed with the recycled gas and preheated to reaction temperature prior to contact with the catalyst in the feed bed reactor and regenerative heating reactor system. There are a pair of reactors which maintain an adiabatic cycle with the heat of reaction required during the process because it was endothermic in nature. And 5 to 15 minutes make period equal to the supplied by the combustion of the carbon deposit of the catalyst during this regeneration period that is mentioned in the dotted line, right? Catalyst regeneration. Now, the temperature of the reaction is 650. It may drop to the 550 at the end before switching to regeneration process. And the pressure low, like pressure equals to 120 to 150 atmospheric pressure. The product gases then oil quenched in the quench tower, and those are compressed, cooled, and separated from the light ends. Flue gas is separated from the light end product, and those are stripped and then butadiene tower, those are fractionated. At the top of the product, we are getting butane as a crude. This is further mixing settler. So from the top, the recycled gas can be taken further to the feed point, and the heavier product is taken to the stripper which is having the crude from the absorption using that cuprous ammonium acetate. You are adding it, and there will be extractive distillation with the, and after that the butadiene purified is from this column we are getting as a top product as butadiene, which is our required, and then NH3 is NH3 still from that NH3 can be recycled to this unit. Here we get around 98 to 99% uh, purity of the product by this process. The next process for butadiene production by the oxo-dehydrogenation process, that is butane, it reacts with oxygen and it forms this. Okay, now coming to the flow chart, you can see that the butane is preheated, and then now oxo-dehydrogenation reactor it is fed and oxygen is also fed, and then it is quenched. This is the conventional dehydrogenation reactor. It is quenched and then it is followed by absorber stripper depropanizer to eliminate the propane, and then butadiene extractor, butadiene by conventional hydrogenation and butadiene by oxy dehydrogenation process. We are getting butadiene as a product. The next process is butadiene production from the ethanol. It has similar kind of like dehydrogenation process. Ethanol, it produce this, and then dehydration is occurring of the same product, and then it is producing the butadiene. Let's now discuss about the process. Now the ethanol is vaporized and it is fed to the dehydrogenation unit, where the dehydrogenation catalyst is also present. It is occurring at a 260 to 290 degrees Celsius to produce the pure acetaldehyde. Now the excess alcohol is mixed through the process, and then it is fed to the fixed bed converter. Excess alcohol and excess acetaldehyde is mixed and it is fixed bed converter, where there is tantala and silica catalyst is present in the fixed bed converter. Pressure is atmospheric pressure. Temperature is 325 to 350 degrees Celsius. The conversion is 28 to 30% per acetal based on the acetaldehyde is obtained, and the reaction goes occurring. Unreacted at ethanol as acetone can be separated out and recycled back to the fixed bed. Now there is a series of distillation column to separate out these products. So here the butadiene we can separate out as our desired product. So thank you. This is up to this class. So we in this class we have discussed about the C3 petrochemical products. So in the next class we will be discussing the rest of the portion of this petrochemical industry. The next class will be the next week Friday. So thank you for today.